Today we'll be doing some theorem, including geometry, grade 11 stuff. Remember guys, whatever that we're doing here, we still need it in grade 12. So make sure you don't forget anything. Or if you do forget, come back, watch the video again, remind yourself. Because this thing, when you reach grade 12, even if you do have someone you know who's doing grade 12, tell him or her to come and watch these videos, revise, because you're gonna need this type of information in your grade 12 stuff, as much as it's the grade 11 information, but you're gonna need it in grade 12. Let's come back. Theorem number 6 now, where it's saying an exterior angle of a cyclic quadrilateral. The exterior angle here is equal to the interior opposite angles, the interior but opposite angles. That's what it's saying. It's saying an exterior angle of a cyclic quadrilateral. Now it's now a cyclic quad, but we have this exterior angle here. It's saying this angle here is equal to the interior but the opposite interior angles. How can we prove that? You don't have to know how to prove it, but let's just show you how to prove this theorem. We know that A, B, C, which is our given A, B, C, D, it's a cyclic quad. We know that. Required to prove, we must prove that C1 is equal to angle A. That is what is required us to prove. Let's prove. Then there's no need to do any construction on this one. We know that angle A welingana or angle A Mount Plaza no angle C2, they give you 180. This one, when you add with this one from the previous theorem, opposite angles of a cyclic quad. Theorem number 5, opposite angles of a cyclic quad add up to 180. And also we know that C1 plus C2 is a straight line. Now this, then if it's a straight line, C1 and C2, they give us 180, which is a straight line. I told you guys there are many things that add up to 180, so must be specific which one are you talking about. Straight line. So now if this and this are the same, meaning they cancel each other, then A is equal to C1. I hope you understand that one, because this one and this one is the same, they're gonna cancel each other, and then what is going to left is that A is equal to C1. And now we know that this one is equal to this one. The exterior angle is equal to the interior but the opposite angle. Coming here to the converse of theorem number 6, what is saying is just basically saying you prove a cyclic quad here like the other ones, where if you prove that if this angle here is equal to this, then therefore A, B, C, D, it's a cyclic quad. So if C1 here is equal to, if C1 is equal to angle A, Therefore, A, B, C, D, it is cyclic quad. You have to prove it. This is one of the ways where they're going to ask you a question that prove that A, B, C, D is a cyclic quad. You still remember we did the same segment where you prove a cyclic quad. There you also did in two opposite angles of a cyclic quad add up to 180. You need to prove also that one where you prove cyclic quad. Now proving another again a cyclic quad on this one where the exterior angle is equal to the interior opposite angles. You prove a cyclic quad also that those angles are equal. Three different ways of proving a cyclic quad depending which one do you have in that case. I hope you understand, guys. Okay guys, now we'll be focusing on doing the examples, applying the information that we just learned right now. We know that U, D, E, F, G is what? It's a cyclic quad. Cyclic quad, two opposite angles of a cyclic quad add up to 180. Exterior angles of exterior angle is equal to the interior opposite angles. The exterior angle is equal to the interior but the opposite one. That is what cyclic quad is saying, the theorem that you just did now. So in order for us to find y, we can just say 105 is equal to y exterior angles of a cyclic quad, and in order for us to find the x yalingana nobani 188 y exterior angles of a cyclic quad. This one is equal to this one is equal to this one. I hope you understand, guys. Coming to this one now, we know that UPTRQ is a cyclic quad. Cyclic quad, two opposite angles add up to 180, and the exterior angle is equal to the interior but opposite angles. So we know that UTRS is equal to UAY exterior angles of the cyclic quad A, which is 1 1 1 2. And then in order for us to find UB plus UT is equal to 180 y opposite angles of a cyclic quad add up to 180. So UB plus 92 is equal to 180 opposite angles of a cyclic quad. Then B is equal to 180 minus 92 give us 88. And this is how we apply our theorem. Exterior angles is equal to the interior but opposite angles. Two opposite angles of a cyclic quad, they add up to 180. Hope you understand that part, guys. Thank you. Okay guys, we'll do just the last example under theorem number 6, where it's saying B E D C is a cyclic quad. So B E D C is a cyclic quad. If we know they have a cyclic quad, two opposite angles they add up to 180. Two opposite angles they add up to 180. If you also have the exterior angle, so this exterior angle is equal to the interior but opposite angle of it. Exterior angle is equal to the interior but the opposite one. I hope you understand that one. You don't make a mistake there. Now another thing that we do have, we know that O is a center. If O is a center, somewhere somehow we must have our radius 8. What is the radius here? OE is a radius and OB is a radius. But this radius we have pass through what? Our center. If we do like we center here to that, there somewhere somehow we do have a diameter here, which means this is a diameter. If we have a diameter, let's check, do we have a semicircle? Semicircle, yes we do, because this part here must be touching our circumference in order for us to find the semicircle, because sometimes it doesn't have to. Sometimes if it doesn't touch this circumference, that means this is not a semicircle. It has to touch where it is circumference to be a semicircle. If this is a semicircle, now we know that y2 is equal to 90 degrees because angle in a semicircle. So y is equal to 90 angles at a semicircle. Just using our theorem, guys. Just using our theorem. Just using our theorem. And another thing, we know that UP1 plus ubani x, they add up to 180. But now we don't have UP1. We need to find UP1 in order for us to calculate what? X. How do we find UP1? We do have this end here, which is ABE, which is this one. So straight line, this angle plus P1, they give us what? 180. So we can find P1 by saying 125 plus ubani P1 give us 180. Why? Because of a straight line. Then P1 is equal to 180 minus 125. 180 minus 125 is 55. So P1 is 55. If P1 is 55, we can say now P1 plus X are equal to 180. Why? Two opposite angles of a cyclic quad, they add up to 180. Then we find our x now. 180 up1, which is 55, so it's going to be minus 55, which is x. Then 180 minus 55 ubani to 125, which is going to be 125. I hope you see I made a long way where this one is equal to this one, which is the opposite exterior angles of a cyclic quad. Exterior angles of a cyclic quad. But I did the long way just to show you guys there are many ways of doing it, like many ways. There's not always a one way of doing it. But now if we have B1, now B1, we're gonna need it to calculate what Z, since this one is what? A triangle. Triangles and the angles in a triangle add up to 180. So we can say up1 plus ubani z2, which is this angle here, plus y 180, which is just sum of a triangle. up1 ubani is 55 plus z plus y, which is 90, 180, 55 plus 90, 145, so 180 minus 145, our z is equal to 180 minus 145 is just 85. I hope you see it, guys, and I hope you understand it. It's very important that you understand it. You analyze your diagram. And you practice Euclidean geometry. Euclidean geometry needs you to practice it. It's not difficult, but you must practice. Practice. Thank you so much. Makebalo, mthanda kakhulu.